Hello everyone. So after from the lecture series from lecture 1 to lecture 6, we had discussed about the theoretical concept of the digital modulation techniques, where we discussed about the basic concepts of the digital modulation techniques. Then we studied in detail about the BPSK, QPSK, offset QPSK, M-ary PSK, M-ary CAM, that is a QAM, then BFSK or FSK, what we say. Then in the non-coherent modulation technique, we discuss about the FSK and DPSK. So on the basis of some of the topics there, we will be solving some problems. So at present, what we require is some formulas there. So for PSK, we have derived it. P is equals to Q of square root of 2 EB to the base divided by N naught. 2 EB by N naught. But when we are dividing in terms of a complementary error function, that has to be, so what I have done in a shortcut manner, I have taken it 1 by 2. So P is equals to 1 by 2 complementary error function of square root of EB by N naught. Similarly for QPSK, we have derived P is equals to Q into the square root of 2 EB by N naught. So when I take it 2 here, since this is a 2 bit, 2 by 2 get cancelled. So P is equals to error function, complementary error function, square root of EB by N naught. For FSK, P is equals to Q into square root of EB by N naught, and P is equals to 1 by 2 complementary error function of square root of EB by 2 N naught. Okay, so if we get 2 here, 2 and 2 get cancelled, so we will get EB by N naught there. Okay, so this is for the coherent detection, and P is equals to 1 by 2 into e to the power of minus EB by 2 N naught. This is for non-coherent detection. Similarly, for DPSK, P is equals to 1 by 2 into e raised to the power of minus EB by N naught. This is with respect to the modulation techniques. Now, just some other general formulas, that is EB is equals to P into TB, P is equals to AC square by 2, bandwidth is equals to 1 by TB is equals to RB. Error function of U is equals to 1 minus complementary error function of U. So this is in general we are taken. You know what about this one? If you don't know about these formulas, please go through the lecture 1 to 6 and then come to the lecture 7 so that you can solve the problem easily. Okay, now the first problem. The binary data is transmitted over AWGN, that is a additive white Gaussian noise channel using BPSK at a rate of 1 Mbps. It is desired to have an average probability of error PE less than or equal to 10 to the power of minus 4. Noise PSD is N0 by 2 is equals to 10 to the power of minus 12 watt per hertz. Determine the average carrier power required at receiver input if the detector is of coherent type. So that is coherent type, and they have given that error function of 2.8 is equals to 0.9998. So this is the question. We have to first list out what are the given things there. So first they have given it as a RB is equals to 1 Mbps, that is a rate of 1 Mbps. BPSK transmitting over rate of 1 Mbps, that is RB is equals to 1 Mbps. Then we can calculate with respect to RB, that is TB is equals to 1 RB, that is equals to 1 by 1 into 10 to the power of 6. So keep it simple, we'll see it later for what is required. So then N0 by 2 is equals to 10 to the power of minus 12 into is what given as watt per hertz. So we have to take, I want N0 only. N0 is equals to 2 into 10 to the power of, because I am cross multiplying here, 2 into 10 to the power of minus 12 watt per hertz. And probability of error is less than or equal to 10 to the power of minus 4, and error function of 2.8 is equals to 0.9998. 0.9998. That is, for BPSK system, P is equals to the 1 by 2 error complementary error function of square root of EB by N naught. This is what the formula we have written there, right? So P we know 10 to the power of minus 4 given is equals to half into complementary error function of EB by N naught. So EB also not known, we know N naught. So we need to find the EB. For that, what I will do, error from complementary error function of square root of EB by N naught is equals to 2 into 10 to the power of minus 4. So I'll go with the formula that error function of U is equals to 1 minus complementary error function of U. So what is the complementary error function of this one? So U is equals to square root of EB by N naught. That is 1 minus 2 into 10 to the power of minus 4. So what I'll get, error function of U, that is the error function of square root of EB by N naught is equals to 0.998. So what is that? We have got that error function of U is equals to 0.98. So what is the value of U now? That is error function of 2.8 is equals to 0.9998. This is what we are given in the question, that we have to be assumed. So that purpose, square root of EB by N naught is equals to 2.8. What I need to find? That is the thing. Okay, I need to find the power. What is that? I need to find the power. For that purpose, I require EB. So EB by N naught is equals to 2.8 the whole square. I am removing the square root here. So EB is equals to 2.7.84, the square of the 2.8 into N naught. You know the value of N naught, 2 into 10 to the power of minus 12. What is EB? P into TB. So I required a P, so I'll substitute TB here. So what is this value when multiply? 1.568 into 10 to the power of minus 11 is equals to 1.568 into 10 to the power of minus 11 into 1 into 10 to the power of 6, because TB is equals to 1 by 1 into 10 to the power of 6. So that will become in the numerator. So what is the answer? Is equals to 1.568 into 10 to the power of minus 5 watts. Next, in PSK system, binary 1 is represented by S1 of t is equals to A cos omega Ct, and binary 0 is represented by S2 of t is equals to minus A cos omega Ct. Is transmitted over a AWGN channel at a 0.2 millisecond. The carrier amplitude at the receiver is 1 millivolt. Noise PSD is 10 to the power of minus 11 watt per hertz. Find the average probability of error for coherent PSK detector. Given error function of 2.236 is equals to 0.99959. Okay. So what they have given, that we have to list it out. S1 of t is what? A cos omega Ct, that is for bit 1. S2 of t is equals to minus A cos omega Ct, that is for 0. The time they have given it as the TB is equals to 0.2 millisecond. And N0 is equals to N0 by 2, usually this is represented N0 by 2 is equals to 10 to the power of minus 11. So that represents N0 is equals to 2 into 10 to the power of minus 11 watt per hertz. So we have to find probability of error, that P is equals to what, and A they have given, that is 1 millivolt. Okay, that is the value they have given, that carrier amplitude at the receiver is of 1 millivolt. So that is A is equals to 1 millivolt. So I can get that P is equals to A square by 2, that is 1 into 10 to the power of minus 3 the whole square divided by 2 is equals to 0.5 into 10 to the power of 6 watts. Then EB is equals to P into TB, that is equals to 0.5 into 10 to the power of minus 6, and T is equals to TB is equals to 0.2 into 10 to the power of minus 3 is equals to 1 into 10 to the power of 10 minus 10 joules. So for PSK system, P is equals to 1 by 2 into error complementary error function of square root of EB by N0. This we know. EB we know, substitute 1 into 10 to the power of minus 10, N0 you know 2 into 10 to the power of minus 10. So that is half into the error complementary error function of square root of pi. So square root of pi is what? 2.236. So complementary of error function of 2.236 is been given. That is, what is that? 2.236 is equals to 1 minus error function of 2.236. They have given the error function, not complement error function. So 1 minus 0.99959, that is equals to 4.1 into 10 to the power of minus 4. So substitute this value here. So that time it will get me PE is equals to 0.205 into 10 to the power of minus 3, and it should be represented as watts. No, sorry, probability of error cannot be represented any bits. Okay. Now the next question, the binary data are transmitted at a rate of 10 to the power of 6 bit per second over a microwave link. Assuming channel noise is AWGN with 0 mean and PSD at the receiver input is 10 to the power of minus 6 watt per hertz. Find the average carrier power required to maintain an average probability of error, that is P less than or equal to 10 to the power of minus 4 for coherent binary FSK. So we need to find the probability of error. Determine the minimum channel bandwidth required. Assume ERF, that is the error function 2.8 is equals to 0.9998. Now, what are the given things? First we need to calculate. So RB is equals to 10 to the power of 6 bits per second. Then TB is equals to 1 by RB. So 1 by 1 into 10 to the power of 6. N0 by 2 is equals to 10 to the power of minus 6 watt per hertz. So the N0 is equals to 2 into 10 to the power of minus 6 into watt per hertz. So P is equals to 10 to the power of minus 4, less than or equal to minus 4. So I can take it directly. So what we need to find? The power. What is the power and the bandwidth? So what is they have told? Average probability of error they have given. Find the average carrier power. So that is P, and what is the minimum bandwidth channel bandwidth required? That is a PT. For FSK system, P is equals to 1 by 2 into complementary error function of square root of EB by 2 N0. So P is equal to 10 to the power of minus 4 is equals to 1 by 2 complementary error function of square root of EB by N0, 2 N0, sorry. That is complementary error function. That is what is square root of EB by 2 N0 is nothing but 2 into 10 to the power of minus 4. So I'll go by the principle error function of U is equals to 1 minus error complementary error function of U is equals to 1 minus 2 into 10 to the power of minus 4. Okay, that is what the value what I got here, that I'll be substituting here. So error function of U is equals to 0.9998. So that is U is equals to, what is that? Error U value is 2.8. So square root of EB by 2 N0 is equals to 2.8. So 2 pi EB by 2 N0 into 2.8 the whole square, that is 7.84. So EB is equals to 2 into 2 into 10 to the power of minus 6 into 7.84. EB is equals to 31.36 into 10 to the power of 6 joules. So we got EB. So I need to calculate P. So P is equals to EB by TB. So I got it from EB is equals to P into TB formula there. So EB into EB by TB is nothing but 1 by TB is RB. So EB into RB. So EB is 31.36 into 10 to the power of 6 into RB is what? 1 into 10 to the power of 6. So P is equals to 31.36 watts. So BT is equals to what? RB. As we know, BT is equals to RB. So bandwidth is equals to 1 megahertz. Looking at this value. Okay. Now another problem. A binary FSK system transmits data at a rate of 10 to the power of 6 bit per second over an AWGN channel. Max PSD is 10 to the power of 10 watt per hertz. Find the average carrier power required to maintain an average probability of error PE less than or equal to 10 to the power of minus 4 for non-coherent binary FSK. Determine the channel bandwidth required. So I required a BT and a P. So RB is equals to 10 to the power of 6. TB is equals to 1 by RB is equals to 1 by 1 into 10 to the power of 6. M0 by 2 is equals to 10 to the power of minus 10 watt per hertz. And N0 is equals to 2 into 10 to the power of minus 10 watt per hertz. So P is equal to less than or equal to 10 to the power of minus 4. I need to find power P, bandwidth is equal to Vt is equal to. For non-coherent BPSK system, we know P is equal to 1 by 2 exponential of square root of minus EB by 2n naught. Okay, so then 10 to the power of minus 4, P is equal to 10 to the power of minus 4, 1 by 2 into exponential of square root of exponential of minus EB by 2n naught. So this is 2 into 10 to the power of minus 4 is equals to the exponential of minus EB by 2n naught. So I have to remove this exponential because this is nothing but E. So I have to take log to the base E, or we can take a natural log. Natural log of ln into 2 into 10 to the power of minus 4. Natural log of E to the base E is nothing but 1 minus EB by 2n naught. Log E to the ln E to the base E is nothing but 1. So natural log of E is 1 into minus EB by 2n naught. So minus 8.5172 the value, and minus EB by 2n naught. So minus minus get cancelled. EB is equals to 2 into 10 to the power of minus 10. Then 2 into 10 to the power of minus 10, and then 8.5172. that is missed here. Okay, so when you multiply this, EB is equals to 3.40688 into 10 to the power of minus 9 joules. So this is, we got a E, then EB is equals to P into TB. So P is equals to EB by TB, EB into RB, as we got know 1 by TB is equals to RB. So value of EB is 3.40688 into 10 to the power of minus 9 into 1 into 10 to the power of 6, the value of RB here. When you multiply, P is equals to 3.4089 into 10 to the power of minus 3 watt. So Vt is equals to RB, that is again no 1 megahertz. Now one more problem, that is here we need to conclude one thing. So what is the power required? This just a theoretical what we studied, so you can analyze here. So compare the average power requirements for binary non-coherent DPSK and FSK, and also for the coherent PSK signaling scheme operating at a data rate of 1000 Mbps over a band pass signal channel having a bandwidth of 300 Hz. N0 by 2 is equals to 10 to the power of minus 10 watt per hertz. P is equals to 10 to the power of minus 5. Error function of 3 is equals to 0.9998. So what are the things given there? RB is equals to 1000 bps, TB is equals to 1 by 1000, BT is equals to, it should be 3000 hertz. Okay, it should be 3000 hertz. Then BT is equals to 3000 hertz. And N0 by 2 is equals to 10 to the power of minus 10 into watt per hertz. N0 is equals to into 10 to the power of minus 10 watt per hertz. So P is equals to 10 to the power of 5 minus 5. So what we need to do, we need to calculate it for coherent PSK, FSK and DPSK. We'll see here one by one. Coherent PSK is nothing but P is equals to 1 by 2 error complementary error function of square root of EB by N0. 2 into 10 to the power of minus 5, that is what we are getting, because 10 to the power of minus 5, this value when you multiply, get 2 into 10 to the power of minus 5 is equals to complementary error function into square root of the EB by N0. So directly I will take error function of U is equals to minus 1 minus square root error complementary error function of U. Error function of square root of EB by N0 is equals to 1 minus 2 into 10 to the power of minus 5. This is the value I am substituting here. So after that, the value, what is that? Is nothing but U is equals to that value 0.99998, and square root of EB by N0 is equals to 3. That is what the value. So if is 3, what we got? EB by N0 is equals to 9. If we are squaring it, EB is equals to 9 into N0. P into TB is equal to 9 into 2 into 10 to the power of minus 10. P is equals to 18 into 10 to the power of minus 10 divided by TB. That is again nothing but 18 into 10 to the power of minus 10 into TB is nothing but 1 by RB. That is I am substituting directly RB 1000. So P is equals to 1.8 into 10 to the power of minus 6 watts. Now for the non-current FSK. So P is equals to 1 by 2 exponential of minus EB by 2N0. 2 into 10 to the power of minus 5 exponential of minus EB by 2N0. So taking natural log into 2 into 10 to the power of minus 5, we get cancel only minus EB by 2N0. So the value will be here minus 10.8198 into minus EB by 2N0. EB is equals to 10.8198 into 2 into 10 naught. So EB is equals to P into TP. So 10.8198 into 2 n naught. So P is equals to 10.8198 into 2 into 10 to the power of minus 10 divided by TB. Again I said TB is nothing but RB. After multiplying this value, we'll get 4.3279 into 10 to the power of minus into RB. 4.3279 into 10 to the power of minus 9 into 1 into 10 to the power of 3. So that is the value of RB. So when you substitute and simplify this thing, we'll get P is equals to 4.3279 into 10 to the power of minus 6 watts. So power is being increased here required. Okay. So now non-current DPSK, P is equals to half into exponential of minus EB by N naught. So that is the value 2 into 10 to the power of minus 5 exponential of minus EB by N naught. Natural log, when you take there to remove this exponential, so natural log into 2 into 10 to the power of minus 5 is equals to minus EB by N naught. So we'll get to minus 10 in by 10.8198 is equals to minus EB by N naught. So EB is equals to minus get cancelled. EB is equals to 10.8198 N naught. So I substitute in terms of EB, P into TB. So 10.8198 into N naught into RB divided by this. What we get is a TB. TB is nothing but RB. I'm directly substitute here. So P is equals to 10.8198 into 2 into 10 to the power of minus 10 N naught value. RB is equals to 1 into 10 to the power of 3. So P is equals to 2.16396 into 10 to the power of minus 6 watts. So we can compare those values and how the power consumption is required. So that is how we can analyze the things. Next one, it's one of the very important problem there. Draw the constellation diagram for M-ary clamp for M is equals to 4. Okay, so here M is equals to 4 we have to take in this manner. Okay, that I said in the axis is pi 1 and this is pi 2. So this is pi 1 and this is pi 2. So this is what you are represent here. But why we are doing separate, so that you shouldn't get confused here. Okay, so here it will be like this way. Okay, this is nothing representing here. This is pi 1, but why I represented it different, we should substitute at the end. So how we do calculate this one? How we calculate by M is equals to 4. Okay, I need it for 4 quadrants. See here, I required it for 4 quadrants. This is for 1 quadrant. Sorry. This is 1 quadrant. This is 2nd quadrant. So this is 3rd quadrant, and this is 4th quadrant. So I need to multiply with these values here. This with these points. 1 first quadrant, 2nd quadrant like this, 4th quadrant. So intersection point between these two, 2 into 2 matrix, that will give me a matrix form there. Okay, this 2 into 1 into 1 2 and 1 2. So like that it will be there. So this we got as we are getting into matrix. This is a shortcut method what we can tell. So like that, first we need to multiply this values there, 1 0 1 0. Then first step here, 1 0 1 0. So this like this will take 1 1 1 0. So like that, this value, this with this value, first step. Okay, it's getting confused, so I'll delete all those things. how to get these values, that's what I told, the graphical method. That is what you need to be remembered. So now first one, this into this. In the second method, this into this, because this is common here, right? This is common here, first quadrant, second quadrant. Next one, third, it has to multiply this quadrant into this one, right? So this into this. Okay, this is third. Next, fourth, this into again this. This is fourth. So this is how we calculate. We calculated for m is equals to 4, and we get 4 distinct points here. Okay, we'll see here. The first quadrant, as I said, 1 1 0 0, 1 1 0 0 1 1 1 0, and here in this 1 0 1 0. Okay. And we usually take this, as I explained in the theoretical part, that a distance usually we represent it by d by 2. Next point, 3d by 2. Next, it will be 5d by 2. Like this, it will be in the odd numbers itself. Similarly, it will carry out for even, this is for positive side, and next one will be minus side. Same thing, it will be there. Okay. So the reason for taking a d by 2, that is a distance usually, and we represent in that manner. Similarly, so we multiply here 1 1 1 0. So that is the 1 1 1 0, 1.1111. That is second point here, 1 0 1 0 and 1 0 1 1 1 0 1 1. Similarly, we do it for stage 2 also. That is the next second quadrant what we distribute. That is 1 1 1 0. That will be common. So 0 1 0 0. So 1 1 0 1 and 1 1 0 0, 1 1 0 1, 1 1 0 0. The same as the quadrant matrix. What matrix multiplication there? What we do? 1 0 0 1, 1 0 0 0, 0 0 0. Next stage 3, it's in this format, in the negative side that it will come. So it is 0 0 0 1, and here this what value it was, 0 1 0 0, 0 0 0 1. Next one 0 0 0 0, next one 0 1 0 0, next one 0 1 0 0. So that is what we are representing in the third quadrant. Next, in the fourth quadrant, 0 0 0 1, the same thing what we are taking it here. Next one 1 0 1 1, so 0 0 1 0, 0 0 1 1, next 0 1 1 0, next 0 1 1 1, 0 1 1 1. After getting the fourth quadrant, we represent all those things here like this. We are merging this pi of 2 and pi 2 axis and pi 1 axis here. The same thing what I told, d by 2 3d by 2, d by 2 3d by 2. Same thing, if it was next 3d by 2. After merging all those things, we get a 4:4 matrix here. You can see it, observe. This is 4 constellation diagram. But this is a matrix which we, the constellation what we saw in the theoretical part there. Okay, but when we plot it for the 4 query plan, we will get this m is equals to 16, the signal space diagram, because 4:4 is nothing but 16. We are drawing the constellation diagram for 4 query cam, but when you plot it in all the 4 quadrants, that time it is showing as a signal space diagram for m is equals to 16. And this is what the important we to take, that code words obey the gray encoding rule. You can observe it here. The gray code has been observed not only for within each quadrant, but also we move from one quadrant to another. The quadrant rule has been achieved. Okay, that is 0 0 0 1 1 1 then 1 0. That's the quadrant we usually choose it. You can check here. Okay. Next, for a binary sequence, okay, this is one of the very important terms. They ask the question on this basis, that is explain DPSK and justify with this one, this sequence. So the sequence, find the binary sequence BK 1 0 0 1 0 0 1 1, generate the DPSK signal. So as I said in the theoretical, that the DPSK should have a reference bit be 1. So I am taking it as 1. DK represents the outputted the differentially encoded sequence, and DK minus 1 is what one delayed bit we take. So please go through the theoretical before solving this problem. So what will happen? DK is what? The output is equals to the input sequence BK XNOR of DK minus 1. That's one bit what we delayed it from DK is getting back as a feedback there. And that is the reason what we are taking it as a reference bit 1. Now, so I am taking a reference bit here. Okay, so I am taking it, but what bits we are given here? We call it as a BK 1. See here, you can see it here 1 0 0 0 1 0 0 1 1. So I'm starting it from 0 and ended at 7 bits. So total 8 bits are given. But why I required a DK 1 here is a reference bit, because I required a 1 bit to be given it back, because I required a DK minus 1 to be encoded, 1 bit delay back has to be required. So that time I'll consider the reference bit as DK. This is the reference bit. Okay, and this is just I taken to know, you should not be confused here. The same thing. Now what will happen? So for that purpose I have taken it as a minus 1 bit. So this is what bit I need to calculate. And but what is this? This is the I have taken it as a minus 1. So bits given is 1 0 0 1 0 0 1 1. Okay. So now this is the all our input bits here. Okay. Remember. So now this is what I am going to explain. See here. Be carefully here. So this I'll be shifting it here. So that time it will become from minus 1 to 0. What is that? It's a 0 minus 1 is minus 1 bit. Okay, minus 1 bit is the given here. Please. Now it is 1 and 1. 1 XOR 1 is the similar bits. It is 1. Again I am taking it here. So that time that is the user DK minus 1. What will happen here? 0 and 1 will become 0, because XNOR bits, unsimilar bits will not be same. So unsimilar bits are there, so that time it will become 0. Next it will be given it here. So next 0 input bit, and what we have shifted from DK into DK minus 1 is 0. So shift it here. For 0 and 0 similar bits, it will become 1. Shift it here like that. 1 and 1. What will become? Again 1. Similarly 0 and 1. It is 0 because it is dissimilar. Then 0 and 0 1. 1 and 1 1. And next 1 and 1 1. So this is the bit. So now this is we are done with the differentially encoding sequence. So in the DPSK we have done with the D. Now we have to do the PSK. So now remember the PSK. So what is happening? Remember in PSK, when a bit is 1, it is shifting by 0 degree. So that is 0 radians we are representing. See here, when it is 1, it is shifting by 0. But when it is 0, it is phase shifting by 180 degrees. You can see it here. When a differential sequence is given as 0, it will represent it as a pi, that is 180 degrees. 1, 0, no phase shift. For this bit, no phase shift. For this 0, the phase shift of 180 degrees. For this, no phase shift. For this, no phase shift. For this, no phase shift. So this is how we do the DPSK, and you should know the importance of the reference bit, and then also how this we have done. So this is nothing but short, we can say that this is D and this is PSK. So together we call this one DPSK. So that is what we have concluded. If DK minus 1 and BK are same, DK will be 1. Else it will be 0 if they are both are similar. You can observe it. So that will be called as a XNOR. Okay, so this is what we concluded with the differentially phase shift keying, or differentially encoded sequence is been given to the phase shift keying. So it's a merger of two. That is what, and the extra the theory part have been explained in the theoretical things. So thank you. So hopefully I've covered all the problematics here. So we can go through it, and similar problems will be asked with the different phase shifts there. Okay, thank you.